Okay, so the Malthusian model turned out to be only good on short-term behavior of the population growth and not on long-term behavior. In order to create a better model for the long-term behavior, we need to adjust our assumptions. That population does not just continue to grow at a rate proportional to the population size. So our second model is called the Logistic Model, and it has the same assumption as the Malthusian model, except that only works if the population is small. If the population is small, the rate of growth of the population is proportional to the size of the population. But assumption 2 says that if the population is too large to be supported by its environment and resources, the population will decrease. If the population gets too large, it's going to decrease. That is, the growth rate will be negative. So we're now looking for a new model that's going to grow at a rate proportional to the population size when it's small, will decrease if it gets too big. The rate will decrease if it gets too big. All right, so my parameters now, I'm going to have the same parameters as the Malthusian model. I still have P for population size, T for time, the same K for when the population is small. We're going to have a constant of proportionality. And I have one more that I'm going to add N. And this one is going to be the carrying capacity. This is the size of the population that the environment can support. So we're going to try to use these variables and parameters to write an equation that satisfies those assumptions. So we're going to start with could be like, a million rabbits is what we can support, yeah. So I'm going to start with the Malthusian model. Okay. So that's what happens when the population is small, right? This is how it grows. So I need to adjust this somehow. I'm going to add another term into this equation that's going to cause that needs to be close to 1. Okay, so if I just add another factor here, right? If I just put something else here, this would be sort of the simplest thing I could do. So this is, when you're trying to write a model, you want to make it algebraically as simple as possible and still satisfy the assumptions. So I'm just going to multiply by something else, and this something, I need to satisfy all my assumptions. Okay, so it has to, when the population is small, I want this something to be close to 1, because then it would just be K times P. And it will, those aren't the notes. They're over here. Okay. So I need that something to be close to 1 when P is small, because then we'll just be satisfying the Malthusian model. And I would like it to be close to 0 when my population is close to the carrying capacity, but still less than the carrying capacity, because then my growth rate will be 0. So if I'm at the carrying capacity, I assume I'm just not going to grow anymore. And if my population is bigger than the carrying capacity, then I want this something to be negative, because then my growth rate will be negative, which means my population will be decreasing. N minus P over N. Okay, so let's... Yes, good. Traditionally, the models uses that 1 minus P over N. Yeah. So does that satisfy all of our assumptions? If P is small, if P is a small population, is this thing close to 1? Yep. And if P is big, but still smaller than the carrying capacity, This thing is close to what? 0. And if P is bigger than the carrying capacity, then P over N is bigger than 1, and 1 minus something bigger than 1 would be negative, causing my rate of growth to be negative, my population to decrease. So my model is going to be K times P times 1 minus P over N. So there's a general solution. A solution to the logistic model. Now, finding an analytic solution, sorry, this is not a solution, this is just the model. There's a model. Finding an analytic solution to the model, like with the Malthusian model, is much more difficult. We can't just guess and check and come up with something here. Okay. So guessing the solution is a little harder than with Malthusian. We're going to think about what the solutions will look like qualitatively. So we're going to start by looking for equilibrium solutions. That's constant functions that will satisfy the differential equation. So I'm looking for solutions that look like this. P of t equals some constant that will satisfy my differential equation. So if P of t is a constant, what's dp dt? 0, right?
Oh, yeah.
Yeah. So if P of t is just a number, then dp dt is 0. So let's see if there are any values that will make dp dt 0. We have a formula for dp dt. It's k times p times 1 minus p over n. There are? Well, let's assume k is positive, because if k were 0, when we look at the model, then dp dt would just always be 0, and that would mean that we have a, yeah, so there's two possibilities, yeah. So if we're assuming k is positive, then either k times p is 0, or 1 minus p over n is 0. Solve each of these. P is 0, or n equals p. Yeah, p equals n. So I have two equilibrium solutions. P of t equals 0, and P of t equals the carrying capacity. These make sense, right? If you have no population at all, of course, dp dt is 0. It can't grow, right? Your rate of change of growth is going to be 0. And if your population is exactly at the carrying capacity, it's not going to grow because you can't support anymore, but it's not going to decrease because population is reproducing, right? So these are our two constant or equilibrium solutions. So P of t equals 0 and P of t equals n. I'm going to plot both of them. So here's time, here's population. P of t equals 0 is right here. And here's P of t equals n. If I start somewhere between P of t equals 0 and P of t equals n, I'm just going to grow and approach the carrying capacity. So it's going to be something like that. Or if I already start pretty close to the carrying capacity, it's just going to go like that with no inflection point. Yeah. Yeah. And then if I start above the carrying capacity, it's going to come down to the carrying capacity. What do you think, I guess, in this particular example, starting below 0 doesn't make sense because you can't have negative rabbits. But if we were just talking about this as a theoretical thing, these would go away from that asymptote. Okay. Should have done that in green. So this is several possible solutions, each one corresponding to a different initial condition. Okay, so we can know quite a lot about the solutions to this logistic differential equation without coming up with a formula, without analytically solving it. All we really need to know are the equilibrium solutions. But don't worry, next class we will solve it analytically. But our next model, we're going to adjust our assumptions one more time, because resources and space in the environment are not the only thing that affects the size of a population. Predators can also affect the size of a population. Okay. But the size of the predator population is affected by the size of the prey population. They're very much linked. So you can't have a model that takes into account predators without having a model for the predators that takes into account the prey. So we're going to call the prey rabbits and the predators foxes. Since each population influences the other, we're going to have to set up a model for both populations. In reality, foxes don't really eat rabbits, but this is like the classic variables used for this problem. Okay, so here are our assumptions. We have 4 now. We went from 1 to 2 to 4. We'll just keep complicating the model till we've captured everything that we think is important. So if no foxes are present, the rabbits reproduce at a rate proportional to their population. Okay. Which is the Malthusian model. Yep. The first one. Yeah. So that's like the simplest first one. If there are no foxes, we're just going to assume that they follow the Malthusian model and that they're not affected by overcrowding. Okay. The foxes eat the rabbits, and the rate at which the rabbits are eaten is proportional to the rate at which the foxes and rabbits interact. Okay. So how often they interact depends on how many there are. So rate at which proportional to the rate at which the foxes and rabbits interact. Yes, but if we assume that it's constant, that space is constant, we can just, then really it just depends on how many there are. And there'll be the constant of proportionality that we're going to use is going to, that's the thing that would be affected by the size of the space. Yeah. All right, we're going to assume that without rabbits to eat, the fox population will decline at a rate proportional to itself. Okay, so the fox population is not going to grow unless they have food. It's going to die off. So this is similar to the Malthusian model also. It's just that now we're going to decline instead of grow at a rate proportional to itself. And then the last assumption is that the rate at which foxes are born, so this is the growth rate of the fox population, is proportional to the number of rabbits eaten by the foxes, which by the second assumption is proportional to the rate at which the foxes and rabbits interact. So we're going to try to translate this into a model. We're going to have 2 differential equations, one for foxes, one for rabbits. We're going to choose the variable and parameter names as we go, because sometimes you realize you need another variable as you're writing the equation. It's not always feasible to write down all the variables first. And it seems very complicated, but you're going to be amazed at how we make it into this nice simple model. So let's start with the easy parts, right? The Malthusian model part, assumption 1, says the rabbits reproduce at a rate proportional to their population. So we'll use R for rabbits. So dr dt, this is the rate at which they grow, is proportional to the size of the population R. And then let's jump down to assumption 3 here. the fox population declines at a rate proportional to itself. I'm actually going to use not K. I'm going to use some Greek letters so I don't run out. So dr dt is going to be alpha times r, and df dt. df dt is going to be negative, right? Because without rabbits to eat, it says that it's going to decline at a rate proportional to itself. So it's going to decline, making the rate of change negative. I need a constant of proportionality. Let's use gamma f. All right, so this is the rate of change of rabbits with no foxes. This is the rate of change of foxes with no rabbits. Do you have a question? No. Okay. Now I need to adjust for the fact that these two interact, that there are foxes and there are rabbits, and they are going to influence these two equations. All right, so let's see if I look at assumption 2. Foxes eat the rabbits. Okay. The rate at which the rabbits are eaten, okay, is proportional to the rate at which the foxes and the rabbits interact. Okay, so this is the rate of growth with no foxes. When I add foxes, that's going to slow down the rate of growth for the rabbit population. So I'm going to subtract something here. Okay. Now I need an...
Start out with less foxes and they interact more.
Yeah, yep. So I need some kind of algebraic expression to represent the number of interactions between rabbits and foxes. And I would like it to be 0 if there are 0 rabbits, or 0 if there are 0 foxes. If there are none of either species, then there should be 0 interactions. So we need an algebraic expression that's going to have R's and F's in it, rabbits and foxes, because they're interacting. That will be 0 if R is 0, or 0 if F is 0. And I need it to go up. I need it to get bigger as R goes up or F goes up. R times F. That'd be a great one. So, and then we're going to have a constant of proportionality that's going to adjust things for like how much space they're in and stuff like that. So this will be beta R times F. So this is our unlimited growth, and then it's going to be tempered, right, by the number of interactions between rabbits and foxes, because the more they interact, the more rabbits are going to get eaten. And then df dt, they're declining. They're declining with no rabbits, but the more the rabbits and foxes interact, we're going to increase that growth rate, right? So here we're going to add to the growth rate another variable, another parameter as opposed to beta. It might be a little different for foxes. So we'll call it delta RF. So do you think that this captures our assumptions? Let's go through them. Let's see. If there are no foxes present, then F would be 0. This F would become a 0, and this term would just go away. And I would just have alpha R, which is assumption 1, that with no foxes, rabbits grow proportional to their population size. Okay, assumption 2, without rabbits to eat, the fox population declines at a rate proportional to itself. So with no rabbits, if R is 0, then this term goes away, and I just get negative delta F, which is the fox population declining at a rate proportional to its population size. So, sorry, that was assumption 3. Assumption 2, the foxes eat the rabbits, and the rate at which the rabbits are eaten is proportional to the rate at which the foxes and rabbits interact. So that's this term here. Rate at which the rabbits are eaten is proportional to their interaction. So we're using RF to model their interaction. and we have it being proportional. And assumption 4, same thing. The rate at which foxes are born is proportional to the rate at which the foxes and rabbits interact. So we add a growth rate onto df/dt. Okay? Yep. You mean the constant of proportionality, like beta and delta, you think should be the same? Is affected by the number of interactions. Yeah. So the number of interactions is the same, R times F. But each species it might be affected a little bit differently. Yeah. So they have a different.
R times F is necessarily the number of interactions.
Right. You're right. It works algebraically. Yeah. So that's sort of the trick of mathematical modeling, is to, I mean, you can't possibly count the number of times rabbits and foxes interact. But that number does what we want it to, right? If R is 0 or F is 0, there'll be 0 interactions. The more rabbits there are or the more foxes there are, the number of interactions will go up.
It might be like 0.02 times RF.
Right. Yes, the constant of proportionality is going to make this take care of that. Yeah.
Isn't that something else, which is how the rabbits are affected by their interaction?
Mm-hmm. Yeah. So.
But is it both? It's kind of both.
It's both. Yeah. Okay. We're sort of using beta as a way to make everything okay. Yeah. Yes, exactly. So we're using beta as a way to roll up the size, the fact that rabbits are faster than foxes, and sometimes they interact, they don't get eaten, and the fact that R times F isn't really the number of times they interact, it just does what we want it to. So we're using beta to adjust. And when you do real mathematical modeling, you do this all the time, and then generally you would play with this in a computer, and you just keep trying different values of beta until it gives you the correct kinds of predictions. So when you write a pair of equations like that, it's called a first order system. It's first order because it only has first derivatives, but it's a system of equations. So it's a first order system of differential equations. The solution to this system of equations is a pair of functions, R of t and F of t. Okay. Since the two functions depend on each other, you can't just solve one and then solve the other, right? You have to solve them simultaneously. And it turns out there simply is no analytic way to do it. Okay. There is no elementary function that we know about, polynomials, exponentials, trig. There's no combination of elementary functions that is a solution to this system of differential equations. For most parameters, I mean, if we made alpha, beta, gamma, and delta all 0, we could solve it. But for most parameters, there's no way to solve. So we have to use qualitative or numeric techniques. Qualitative, like we just did, find the equilibrium solutions, sketch out what the solutions would have to look like. Or you can use a numeric technique, which is what a computer would do, to study the solutions. So one way to study a solution numerically is to pick some initial values for R and F, use them to calculate values for dr, dt, and df, dt, and then use the rates of change to estimate the values for R and F a small unit of time later. So I'm just going to show you very briefly what it looks like. But generally, we have a computer do this for us, but I'm going to show you what the computer would do. So let's just let the number of rabbits start out at 12 and the number of foxes start out at 2. So I should say this is R of 0 and F of 0. So that means that dr dt And let's let alpha, beta, gamma, and delta all be 1, just to make the calculation a little easier here. So dr dt, which is going to be alpha r, so just r minus rf, and df dt is f, negative f plus rf. So now I plug in values for r and f, my initial values for r and f, and I have 12 minus 12 times 2, which is negative 12. Did I do that right? Yeah. Okay, and then my foxes, I'm going to go negative 2 plus 12 times 2. So yeah, 22. So I can only go 1 time step here because I'm not going to have any rabbits left, right? dr dt is changing by 12 rabbits per unit of time, small unit of time. So 1 small unit of time later, r of 1, if we're measuring in like hours, right? R of 1 would be 0, and now we're at an equilibrium solution. And f of 1, we started with 2, and now we added 22. So we're going to have 24 foxes, and we're at equilibrium. What? No, the foxes are just going to stay at 24.
No, because they don't have.
Oh, you're right, because they don't have any rabbits. You're right. Yes, you're right. Yeah, thank you. Yeah, dr dt is at equilibrium. There are 0 rabbits, it can't be any more, and df dt is just going to decline to 0. So we started with 2. We calculated df dt to be 22, and this is rabbits per unit of time, right? Because change in rabbits over change in time. So take how much you had before, add how much it changed, and you get 24. So we don't have to continue to do this over and over. In fact, we're going to do more with this numerical technique in a couple of days. I just wanted to give you an idea what you would do. It could take a long time to reach equilibrium. Sometimes you don't reach equilibrium. Sometimes you go to infinity. Or so a computer program would be super, super helpful to do that calculation for us over and over and over. So we've seen 3 models: Malthusian, logistic, and the predator-prey model. We've seen 3 techniques for studying their solutions: analytic, where we just guessed and we came up with a formula; qualitative, where we were able to just draw pictures of what the solution would have to look like, even though we couldn't get a formula; and numerical, where you calculate dr dt or df dt at various points in time and use that to project the population sizes forward. So the next 3 sections of the text will further illuminate each of these 3 techniques. This is just a little introduction. And I have on the back of that, on the next page, is a little worksheet on modeling, where I've given you some assumptions, and I want you to try to write a model, differential equation, to model it. So you can work on that one in your groups.